Good morning, everyone. Today, my group and I will be presenting on load measurement using a capacitive transducer. We'll explore how this type of sensor works, its internal structure, real-life applications, and how it is used to measure load accurately. Let's begin with the basics. A capacitive transducer is a type of sensor that converts physical changes, such as displacement, pressure, force, or load, into a change in capacitance, which can be measured electrically. This makes it very useful in precise sensing and instrumentation. Now, how is it built? The structure of a capacitive transducer includes two metal plates with a small gap between them. Between the plates, there is a dielectric material, such as air or plastic. The capacitance of this setup depends on three main factors. First, the overlapping area of the plates. Second, the distance between them. And third, the type of dielectric material used. The working principle is based on the formula C equals epsilon times A over D, where C is the capacitance, epsilon is the permittivity of the dielectric, A is the area of overlap between plates, and D is the distance between the plates. So, as the distance D decreases, say from applying force, the capacitance C increases. So, this principle is actually applied in a bunch of real-life applications. For example, in electronic weighing scales, a load compresses the plates, which changes the capacitance. This change is then converted to a weight reading. In fuel level sensors used in vehicles, the fuel itself acts as the dielectric. And as the level changes, so does the capacitance. Proximity sensors, like the ones you see in hand dryers and automatic doors, work by detecting objects that come near the sensor, which affects the local electric field and, as a result, the capacitance. And finally, in touchscreens, your finger acts as a conductive object that changes the capacitance whenever it touches the screen. So how do we actually use a capacitive transducer to measure load? Well, when a force or weight is applied on the top plate, it pushes the plate downward, reducing the gap between the plates. This leads to an increase in capacitance. Since this relationship is pretty consistent, we can calibrate the system to translate the change in capacitance into a load or weight value. Basically, a capacitive transducer measures load by detecting changes in capacitance that happen because of variations in the distance between two conductive plates. These plates are set up parallel to each other with a dielectric material in between, most commonly air, and one of the plates is mounted on a flexible structure that moves when force is applied. When a load is applied, it causes the movable plate to deflect toward the fixed plate, decreasing the gap between them. According to the equation C equals epsilon A over D, where C is capacitance, epsilon is the permittivity of the dielectric, A is the effective overlapping area, and D is the distance between plates, the reduction in distance leads to an increase in capacitance. This change is measured very precisely using high-resolution electronics. The relationship between capacitance and load is established through calibration, usually by using known weights and recording the corresponding capacitance values. Once the system is calibrated, it can figure out unknown loads by converting the measured capacitance values back into force or weight units using the calibration curve or formula. This method gives you high sensitivity, excellent repeatability, and is really suitable for small to medium load ranges where precision is super important. Let's now look at the advantages and disadvantages. Advantages include, first, high sensitivity. Small movements result in significant changes in capacitance. Second, low power consumption. They work with very little power, which is ideal for portable devices. And third, they're compact and lightweight, making them easy to integrate into small or mobile systems. But there are also disadvantages. They're sensitive to environmental conditions, such as temperature or humidity. The output can be non-linear, so extra calibration is needed for accurate results. And their range is limited, meaning they're really best suited for small to medium loads. To tie this all together, here's an example question. A capacitive load sensor has two plates, each with an area of 20 square centimeters and air as the dielectric. Initially, the distance between them is 2.0 millimeters, and the capacitance is measured to be 8.85 picofarads. When a load is applied, the distance decreases to 1.5 millimeters. We're asked to calculate, first, the new capacitance. Second, the percentage increase in capacitance. And third, using a calibration curve where 1 millimeter compression equals 10 kilograms, estimate the applied load. This demonstrates how a simple measurement of capacitance can be used to determine how much force or weight has been applied. And with that, we conclude our presentation on capacitive transducers for load measurement. Thank you very much, and we're happy to answer any questions you may have.